All right, it is 10:01. It's good to be with all of you today. As we transition, we're gonna go from playing with infinite series in our infinitely long interlude in the middle of the class to our home stretch talking about vector calculus. I think this is one of the most beautiful chapters in the class because it sort of ties almost everything that you've done in calculus together. So you'll see some limit stuff showing up and plenty of derivatives, and the fundamental theorem shows up in new ways, and all that chapter 13 space curve stuff that that sort of disappeared. All of it goes away. We'll end up with or comes back again. We'll hit our multiple integrals with double integrals and triple integrals, all those beautiful things all together at once. But before we start diving into the new material, let's just make sure that we go over our basic announcements. So let's start looking at this chapter 17 on vector calculus. So in this chapter, we're going to study the calculus of vector fields. So these are functions that assign vectors to points in space. In particular, we're going to define line integrals, which can be used to find the work done by a force field in moving an object along a curve. And then we will also define surface integrals, which can be used to find the rate of flow across a surface, which is called the flux. The connections between these two types of integrals and the single, double, and triple integrals that we already met are given by higher dimensional versions of the fundamental theorem of calculus. So our big three theorems from this chapter are called Green's theorem, Stokes' theorem, and the divergence theorem. So if you're kind of wondered what it is to focus in on this chapter, the focal point should be those three theorems: Green's theorem, Stokes' theorem, and the divergence theorem. But today, good news, we're not going to do much in the way of calculus. We're just going to spend our time trying to understand what vector fields are, because they're going to be kind of at the center of the chapter. And rather than doing a whole bunch of crunching, I think I'd like to spend the day trying to visualize what's going on with these fields. And so there's not much in the way of examples to work through, but lots of interactive figures for us to focus on. Are there any questions before we dive into the material?
Chapter 17, right?
This is 17.1, chapter 17, section 17.1.
And what's the section called?
It's called vector fields.
Thanks.
Very good. All right. So we are talking about vector fields, and we've got two objectives for this section. We're going to talk about vector fields and give a whole bunch of examples, and then we're going to spend a little bit of time talking about gradient fields because they're a pretty famous and popular type of vector field that we will play with in this chapter. So in this section, we're going to consider vector functions, or functions called vector fields, that associate vectors with points in 2 or 3 dimensions. So these functions play an important role in the study of fluid flow, gravitation, electromagnetic force fields, and other applications. We generally use the big F right here with the arrow on top to denote a vector field. For 2 dimensions, we have that big F would be equal to little f in the x direction, little g in the j direction, or if you like it in the angle brackets, you can think about it as having an f function giving you the x components and a g function giving you the y components of your vector field. 3 dimensions is the same, except for now you have f for x, g giving you the y's, and h giving you the z's. And so we call these f, g, and h's the component functions. And we're going to get a couple of examples in a moment, but I think that the notation should be mostly clear that this is just saying how much in the x direction, because there's your I, how much in the y direction, there's your j, and how much in the z direction, because there's your k. questions about the notation so far?
So it seems like the functions all hold like XYZ variables, but only
Mhm.
specific functions will actually give us the I, J's, and K's.
Correct. And if you could just hang on for a minute, I think we'll see a whole bunch of examples of what the big F's might look like and what the little F's and the little G's would look like as well.
Okay.
Yeah, so just hang with me. It's good, but you're correct. All right, so what follows are a number of examples with some commentary. So let's see.
I like vocabulary words.
Vocab words are nice. Very tight. Okay. So here is an example of a radial vector field. Radial as in kind of going out from the origin. You can see all these vectors are going to point away from the origin. You can see that as we move around our point. And so you can imagine that we have a whole bunch of dots, like at all, maybe all the integer pairs or whatever, and you could say, well, what's the vector that would show up at each one of these points? And the vector, so for example, here would be, this would be at x equals 1, y equals a half. And so the vector field, your big F, is equal to the angle bracket 2x comma 2y. So in this particular case, the 2x would represent f of xy, and the 2y would represent g of xy. Okay. And so we could find all those vectors at all of these different points. And if we found these vectors at a whole bunch of different points, that would give us a way of visualizing the vector field. So here's that vector field. One of the things that you'll notice about this is that the vector that I'm dragging around is a lot longer, and it would overlap, like let me see if I can change my color. This vector that I've drawn is a lot longer than the ones that are nearby, and they would all overlap. And so one of the things that's pretty standard when you graph these is that they will scale the vectors. Scale vectors so they're all visible. And so what does that mean? It basically means that they would find, graphically, you sort of find the longest vector and give that some known length, and then make all the other lengths proportional to the long ones. So knowing this length here, measuring that length with a ruler isn't going to help you very much, but what does help is knowing that that one is about twice as long as the one that's in here. So we're sort of looking at the proportionality of the lengths. Does that make sense on the scaling?
I got a question.
Mm-hmm.
Would we ever see it the opposite, where it's like greater towards the origin and less on the outside?
Sure. Yeah, we could have them get infinitely long right here at the origin and be short elsewhere. So maybe you'd have big F equals, I think 1 over x comma 1 over y would accomplish that.
Oh yeah, that makes sense. Thank you.
Very good. Other questions about how the vector field is set up and created? Okay. So
Quick
oh,
question.
go ahead, Titus.
So at what, this is just a general question, but at what point of the graph are the vector fields grow infinitely long?
In this particular graph, like in this graph, is that what you're saying?
Okay, yeah.
Yeah, so the vectors are never infinitely long here, except for, I mean, you could think about it, I suppose, as x goes to infinity. Well, be careful here. It's not. As x goes to infinity, then the magnitude of f would also go to infinity. I'm not quite sure what that would represent, but the point isn't really like what's the length. We're not really looking at limits at this stage. We're just trying to understand what vector fields look like, and specifically in this case, a radial vector field where everything is spreading out from the origin. Did that answer your question?
Sure.
Very good. All right. So one important note here is that perhaps a little bit in this section, you'll have to sketch some things, but in general, you will not have to sketch very many vector fields in this class. So this class isn't about sketching vector fields. You can imagine that if you tried to sketch this, you could be there all day, because how many vectors do you need to actually draw in order to come up with a good picture? What I want you to take away from today is some visualizations and some labels, so that you don't have to sketch things, so that when we're doing examples later on, you go, oh, I understand what might be going on in this situation because I can visualize what some of those vector fields would look like. And to that end, I would encourage you to mess around with these interactive figures. I know that I give you a homework point when you download them, but I think a lot of you are, clicking on the link and then just moving on and not thinking about them. In this particular chapter, I think that it will help you to visualize if you just start messing around with things. So it's not hard, but it is different. Yes, Jason, that's right. I do know. At least I know that. Okay, let's go on to the next couple of examples. So 3 more examples. Oops. Not one end. Okay. This is what's called a shear vector field. And so notice in the shear vector field, there's no x component in this particular example. So little f was equal to 0, but our g is equal to x. And so this will say there's going to be no x component. It doesn't matter where we go. The vectors are always going just up and down. And then the vertical component depends upon how far we are. So notice here we're 2 units to the right in the positive x direction, and our vector is length 2 going up. Here we're 1 unit on the negative side of, for negative x's, and our y component is -1. It's going down by 1. And so you have this idea of a shear field where, and I'm not an engineer, but as I recall, this is talking about like a shear stress. This might help you to see it. So if you're talking about shearing something off, you imagine having one force that's kind of going up and another force that's going down, and the question is, does it kind of like snap in the middle, so to speak? And so that kind of gets at the same idea. I hope it's clear that you could also have a shear field that was going the other way if you were so inclined, or some variant thereof. We also have this idea of flow curves. And so imagine that you took a little BB and you dropped a little floaty thing into this field, and you asked what happened to it. Well, since in this case it's close to the y-axis, but a positive, it would move north and it would move there slowly. If we dropped our little floaty device over here farther in the positive x-axis, we would still go north, but now we would go more quickly. If it was on the left side, we drop a little floaty in, it would go south. And so that's this idea of a flow curve. Like what would happen if you put put a dot into the field and asked where it went. Questions? Yeah, it's a swimming pool for swimming laps. And I think that this would be me right here. And this would be where I need a breather. So anybody here do swim team and they can like knock out their laps like crazy? Nice. All right. Yeah, so those of you that have spent time in physics and you've played with electrical charges or magnetic fields or things like that, you're going to see all of that stuff coming to bear. So those of you that have had lots of physics, lots of engineering, by all means, feel free to chime in and feel free to chime in and help those of us that are more mathematician and less physicist. Next example, questions about this one? Yeah, Damon, you're saying I was pretty good, getting good with writing with the mouse. That must have mean it was pretty bad in the beginning. All right, next example. This is channel flow. And so you can imagine that, that you have like the bank of a river here. I mean, the bank of the channel. This is where math and reality don't always work. And same thing here would be the lower bank. And so you can see that there's all the flow is going in the same direction in between the channels. And in this particular case, I believe when we pop out to the other side, they won't let us pop out. But if we popped out to the other side, you could imagine that you would end up with a negative, you'd have flow going the other direction if the manipulate allowed it. So should be clear, where's the flow the fastest?
In the middle?
Oh, y equals 0.
Yeah, y equals 0. And should be pretty clear that we are going from left to right. So you can look at those curves. Oh, it's a channel, right? It makes sense that our flow lines would all be going left to right. But the flow lines don't capture the speed at which things are happening. The vector field's a little bit better for that. It shows you that things are kind of relatively slow next to the bank, but then they're faster here at the center. Which kind of makes sense, right? More friction, I don't know what you call it in water, but friction type stuff here at the edge versus the fast flow in the center of the canal. Questions about channel flow? Very good. All right. This next one is rotation, and probably blow your mind. You can imagine that if you want to if it's with a name like rotation, the vectors are all going to kind of point around. In this case, they're going counterclockwise. Notice that if we're close to the origin, we'll have small vectors. If we're far from the origin, we'll have fast faster vectors. Would this be like a whirlpool? What do you think? Is this like a whirlpool?
Like spiral?
No, it would be
The-
like an inverse whirlpool because the currents are faster at the center with a whirlpool.
Yeah, exactly. So in a whirlpool, things are spiraling in, right? And
Don't
so
we
it's getting
also have-
faster and faster. But
Yeah,
in this, go ahead.
sorry, isn't that also like with whirlpools, like a Fibonacci thing where it's not quite like this one?
Yeah, we could use the golden ratio and the Fibonacci sequence to generate kind of a spiral, but I'm just thinking about it in a more general sense.
Is this assuming that the it has a constant angular velocity?
I don't know would probably be my best answer. I think so, but I don't know for sure. I think in this particular example, what will happen to our flow curves? Are our flow curves going to spiral in, spiral out, spiral at all? What do you think?
I don't think they'll go in. I think they'll just continue going in whichever way they were going.
Okay. Yeah, so in this particular case, because of the uniformity of the vector field, you're correct, Enrique, that wherever you put that, that floaty, it's just going to keep going in loops for forever. So it's not really a whirlpool in or out. In order for that to happen, it would have to be kind of faster on one side than on the other side to kind of force it in or force it out. Or have some component that was pointing in or out. Cool. All right, so that was shear fields, channel flow, and rotation fields. I want to focus in a little bit more on these radial and rotation fields, and specifically talking about vectors that are normal or tangential to the curve. So this is example 3 in the notes, and I want 8. Okay. So this particular example is a little bit different. So first thing I want to point out is that I have my x comma y in the numerator, and then in my denominator I have root x squared plus y squared. So that tells us that in this particular vector field, all of our vectors are which kind of vectors?
Unit vectors.
Exactly.
Yeah.
Our old friends. So we have unit vectors. I think that those are going to be the, I think that's the red ones. So notice that the red vector f is staying the same length regardless of what's going on with the blue one. Notice that it's also going to be, it's radial, i.e. it's perpendicular, or it's radiating out from the origin. Okay. And let's focus in here a little bit on this puppy. What does this nabla symbol tell us we're using? You guys remember?
Gradient?
It's a gradient.
It's a gradient. Good call. And I think this might be the first time we played with the gradient in this class. Do you remember the formula for the gradient of f?
Derivative respect to x and derivative respect to y.
Yeah, so it's a vector quantity, and we'll have the partial with respect to x, partial with respect to y. Thanks, Vu. Okay, so here's our gradient. Except for, I guess they were using g's over there, so maybe we should gify it.
Chuckle.
All right. Let's see if we can, let's see if we can calculate that gradient from this formula. So if we have big F is the thing up above, then, and we wanted to find the gradient of that. Oh, that is a gradient. I was trying to figure out what's the field that we're working with.
You could take the integral.
Well, that's a good call, although I'd rather not do that today. But what happens when you integrate a gradient? So this is going to give you, do you guys remember what kind of function? So if you integrate a gradient, it will give you what's called a potential function. And for those of you that have had a whole bunch of physics, as soon as you see that word potential, what do you start thinking about?
Energy.
Energy. Yeah. Now, the concept of potential in calculus here is a little bit more general than the idea of potential energy, but I think that the basic gist, or those things that you've learned about potential energy in physics will help you in this class as well. So they're not exactly the same, but there's definitely some parallels. Okay. So what I want to point out here is that if we have a radial field, that all of our vectors are going to be perpendicular to the curve, to the level curve. If we have a rotational field, then all of our vectors are going to be parallel to or tangential to the black circle. So notice here, we're always going to be parallel to the radial, sorry, in a rotational sense, we're always going to be parallel to that rotation. If we are in a radial field, we're always going to be perpendicular to that circle that's there. So this is going to be a big deal because generally speaking, we're going to be looking for how much stuff, if you will, is flowing through a surface. And this will give us what we're going to later talk about as the divergence or the flux, talk about this thing called flux. Whereas, so that's kind of in this radial example. Whereas if we're in the rotational example, notice we're going parallel, and this is going to tell us something about the work that is done. And so we'll see a couple of our, and I think also the curl. Curl is the quantity, work is the physics thing. Here, div is, or divergence is the quantity, flux is the physics thing that we're going to talk about. So this, we don't have to do anything with them yet, but this is kind of a hint of where things are going. Questions?
What sorts of stuff are we going to be asked to do with this on the homework? Because it doesn't really seem like traditional homework examples.
Yeah. If I was more on top of it, I would have a clear answer for you. But I think that you're probably going to be asked to do a whole bunch of matching. Like, hey, here's the field. Which of these graphs is right? Or things along those lines. Or if you put a bobber in here, where would it go? Draw a few flow lines, those kinds of things. There's not much calculus in this section. It's just kind of a visual section.
Yeah, thank you.
You're welcome.
So do you know what the skills check is going to be like then for this? Or
I think others of you have already played with the skills check. Do you want to answer that one?
They ask you to integrate and find the work. It's really easy. just take your time. It actually really easy.
Okay, thank you.
Yeah.
It's like 7 questions.
Yeah. The main things that we're going to spend time on in this chapter is lots of stuff about work, lots of stuff about vectors. And so it's kind of what would make the most sense. All right. Everything we've done so far is in 2 dimensions. It's going to blow your mind, but you can also do this all in 3 dimensions. So where's that first picture? So for example, here is oh, thanks, Twee. Write an equation for a normal line. That'd be another example. So here's a vector field in 3D, which to me looks a little bit like the graffiti that's in my neighborhood. Like, it doesn't make a lot of sense. But fortunately, we're in the world of interactive stuff. And so you can see that what's happened is they've sketched a 3D vector at all the grid points. We could add more grid points if we wanted. And it should be clear how this might, like what this would look like. You can start to visualize it. I think it's safe to say sketching these by hand is not terribly helpful, and even graphing them in 3 dimensions isn't that helpful, because it's hard to know what this would tell you, other than I suppose it might tell you something like the flow lines look like they're kind of going like up, something like that, and maybe they're coming out as well, going back. But it's not, the graphs are interesting, but they're not terribly helpful. There's just too much going on in 3 dimensions for the graphs to be super helpful to you. They can be a little bit more helpful to you if they're tied to a figure. So for example, in this case, imagine that you have flow going through a pipe. And so we're asking ourselves, what's going on as our flow is going through the pipe? And I think it's sort of like that channel scenario that we had before, where notice you have the slower flow at the edges and the faster flow in the middle. And should be clear, all the stuff's going the same direction. But again, the 3D pictures are really not terribly helpful because they're just so busy. There's so much going on. It's hard to know what's happening. Questions about the 3D pictures?
The first example kind of looked like the virus.
Mm-hmm. Yeah. Yep. I mean, an obvious application of a vector field is you could imagine you've got, I don't know if I can, you've got a picture of America, something like that, lower 48-ish. And you could imagine that we have all those points, and we could ask, at some point we're going to be saying, what happened to the virus? And we're going to say, well, from, it was, how did it travel? And so you could say, well, it was going out from these various places, and it was going in such and such directions, or something like that. And so you might imagine you creating a flow pattern there. But there could be lots of applications for vector fields, but I'm not quite sure. I'm not quite sure how. I don't think that will tie directly into this class, sadly. All right, so all that has been about vector fields. Let's spend a little bit of time talking about the gradient fields. So if f is a scalar function of 2 variables, then we say that del or nabla f or grad f is defined by nabla f equals fx comma fy. Here we're using the i's and j's instead of the angle brackets. Same thing for gradients if you had, if you were in 3 dimensions, but again, much more difficult to visualize. So one thing that's kind of important here to note is that gradient fields are orthogonal to level curves. And so here, the light blue or teal represents the level curves of a 3D surface. And then of course the angles represent, or the vectors represent the gradient field. So let's check our vocab again. So we have some del phi. This is our gradient. And then what do we call the, quote, antiderivative of this thing?
Potential something?
Yeah, so this would be our potential function. Which classes have you found potential functions in? Was that something you did in differential equations? Like, I can't remember. Maybe it's new to this class.
It's not really ringing a bell. Yeah, I think this is the first
Okay.
time.
I remember doing gradients, and I can't remember if it was diff EQ or Calc 3.
Yeah,
I know we did gradient 3.
Yeah, but you didn't go in reverse and have the gradient and try to find the potential function, I don't think.
No.
Okay. Let me give you a spoiler. This is going to come up later, but since we're kind of on the topic. So if you're given that gradient, then that's like a little fx and a little fy. And so what you'll do is you'll start with that fx and you'll integrate it with respect to x. And you'll find a potential like, ooh, did I find it? And now you get an idea, like, but then you realize, wait a second, there's a problem. I don't know if my potential function accounted for the fact for what's going on with the y's. And so you end up differentiating this with respect to y. And that should get you back to your fy. And then you end up integrating again. And with respect to x. And this will give you your actual potential function. This doesn't have to make sense now. I'm just putting it here and bringing it up because it's going to come up in a couple of sections. As soon as I started talking, I realized the reason why this is sounding familiar to me is because I taught Calc 4 in the fall. And so I'm thinking back to fall when I last taught this material. So
this all seems very similar to some stuff in differential equations.
Yeah, I think it is. It's been a long time since I've taught diff EQ. Okay, so back to the picture. So remind me again, what do all these curves represent?
Vectors?
So these are vectors. These are all tied to the level curves.
Level curves.
Of the potential function. So what's happening here graphically, like if we were to graph it in 3D, what's happening in this region here on the left?
Has the same magnitude?
Yeah, like what would the picture look like?
A mountain?
Like a little mountain.
So it would either be a mountain or a
Valley?
Or like a hole, right, of some sort. Okay,
So
so
closed, it would be a depression.
yeah, so it could be a depression if it was down. It could be a mountain if it was up. What's happening here in this region here?
It's flat.
Could be a mountain.
It's
So,
kind of like the ground level, right? Whether it's below the mountain or above the divot.
Well, you can't really tell because it's you know, you don't see the z like axis.
I think
We can assume that
It's
area is
probably
flat, but we don't know if it's higher or lower than anything else.
right. You don't know which way it's going, but it's probably a saddle. So where it's going up on, we don't know which one it is. We don't know if these are mountains or divots, but probably this is a saddle where it's going up one direction and down the other, or up the second direction and down the first. That'd be my guess. Think like a topo map. That's what you got, a topographical map. So I think we'll have Robert as our, I'm guessing, our
Feels like
military.
land nav.
Yeah.
Yeah, land nav all over again. Taught that for 4 years. I'm tired of it.
Nice. Okay, so you don't need to teach it. You can just laugh at my teaching of it. That's fine. Then with that context, what's happening in this region in here, probably?
Like a little valley.
So it's probably either a valley, or what would be the other alternative? It could be a
ridge.
It could be a ridge. Yeah, so it's either a valley or a ridge, presumably. And all this stuff makes me want to go hiking and enjoy this good weather rather than sitting inside my Corona cabana. I mean, not that I don't want to talk to all of you, but looking at this makes me want to check out some valleys and some real ridges, not just maps. Okay, so all that said, these are level curves. What's the relation between the level curve and the gradient field?
They're orthogonal to each other.
They're orthogonal to each other, exactly. So here's the gradient, and so if I put my gradient on any of those level curves, you can see it's pointing perpendicular to the level curve.
Is it direction of steepest slope as well, synonymously?
Mm-hmm. Yeah, so it looks like in this case, we would be going from low to high. So this must be a divot and a divot, whereas this must be a mountain and a mountain. And if we looked at the whole field, you'll notice that those gradients are always perpendicular. Are always perpendicular to the level curves everywhere. Okay. Makes sense? So imagine that we started at some point. Let's make one up. So if we started here here we are in the divot, okay, and maybe we start traveling this way. So we're going to cross, and then we're going to stay perpendicular, and then we're going to. So this is the path of steepest ascent, steepest up, right? And so at each point here, I'm trying to stay 90 degrees, right? I think you would have done this in Calc 3, right?
Yep.
Starts to make a little bit of a curve here. And you can imagine that if water was flowing, it would flow the reverse direction of this, right? Flow downhill, steepest descent, presumably. And so these curves have a name to them. So these are called the equipotential curves. So equipotential curve. And the key with the equipotential curve is it's just going with the gradient field, which is always perpendicular to the level curves. But it's basically saying, what would the flow do if you followed that gradient field? Make sense? Let me show one more picture of that. Where did it go? So here would be an example with those potential curves. So you'll notice that they're always perpendicular to the level curves, and they're continuous. So they are orthogonal to the level curves. They are continuous because things are flowing. I mean, unless things happen to stop, like not much is happening right here at these dips. But they're just growing out and saying this is what's going on if we followed that gradient field. So questions about vector fields or gradient fields? Very good. So I hope that as you went through this stuff, you got to enjoy some pretty pictures and got a little bit of a sense for what these vector fields might look like. But I also hope that today was a relatively tame day. And so I hope that you can see this as a section where we just introduced some new graphing ideas and some new kind of like a sense of motion almost, or force fields to the topic, but we haven't done anything that's terribly complex yet. When we come back tomorrow, we will start talking about what would it take to move a particle through one of these force fields. Right? You can imagine, what does it take to swim across a river, right? That it can be easier or harder depending upon what's going on with the flow rates in the river. So pretty simple stuff. And I would say a nice soft way of starting this section. So as we wrap up, I want to wish you all a wonderful day, and in the spirit of all those topographical maps, may you all find time to practice social distancing, but also get outside and enjoy some of the most beautiful terrain in America that we just happen to all live in the middle of. And that includes Devon and Arizona, even if his is a little bit drier and warmer. So have a wonderful day, everyone, and I will see you all tomorrow.
Take care, Dusty.
Take care.
See you, Dusty.
Take care, Titus. I'll talk to you this afternoon.
Sure.
Questions, Enrique, Evan, Joseph?
Just chilling.
Chilling's good. Pardon me. Joseph, any questions?
Seems like he just logs in to make it seem like he's in lecture. But really...
What do you mean? No, I've been here the whole time. I've been here the whole time. I'm just setting things up for my room.
Yeah, that sounds good, yeah.
Thanks for the lecture, Dusty.
Take care, Enrique.
Thank you, Dusty. Have a good rest of your day.
You as well. Take care.
Second. There we go.